This is Rachel Lohan presenting Lab 2 for Physics 2211, Motion of a Falling Object. Here are the contents of the lab. Getting into it, we have the introduction. The purpose of this lab will be to observe the motion of an object dropped from rest, somewhat slowly, straight down. This motion will allow us to employ tracker and model the effect of drag from a force opposite to the motion of the object. Some of the physics principles that we will be discussing today are Newton's second law of motion, drag force, and gravitational force. Newton's second force affirms that an object in motion will remain in motion unless acted on by a force. Drag force is the resistance force caused by the motion of a body through a fluid such as water or air. Gravitational force pulls objects with mass towards each other, in our case Earth and the crumpled paper. Here are some relevant formulas. We have the position update formula, the velocity formula, the gravitational formula, and the drag force. The details of the experiment are: first, we will record a video of an object dropped falling slowly with a straight path. We'll put the video into tracker software to gather position data and time. Using tracker, we'll use a frame-by-frame analysis to track the object's position at certain times. Then we'll start using GlowScript to code a computational model to match the environment of our experiment and match the initial conditions accordingly. We'll record the data from GlowScript with the simulation and graphs, and then we'll compare the data from each method and form a conclusion. So here I have the tracker video loaded in, and my hand and the floor are the surroundings, and the system is the paper ball, which I drop slowly straight down. So we can see the graph here has our ball falling consistently until it gets to about here where it bounces off the floor. These are the numbers I was able to gather from the tracker video analysis. So I have the total time from the drop to the floor is 1.737 seconds. The initial position starts at 0, 0, 0 meters. Initial velocity, same vector. And the initial mass is 0.003 kilograms, and these numbers will be put into the GlowScript condition code to match the initial conditions. So in this first GlowScript model, this is the model that only accounts for the gravity, not the drag force. I manipulated the model to contain the initial data set in order to best represent the experiment. I also changed the formula, the negative ball mass times the gravity 9.8 meters per second, times j hat to fix our formulas, and then I took the drag force and kept it as 0 to make sure that it wasn't accounted for in this model. Here is the next model. I have accounted for both gravity and drag force in this one. I changed the drag force coefficient, which is b in my model, to be 0.25 using the proper calculations. And you can see that the model is slightly different the graph is slightly different in the way it appears. Here's a comparison of all three graphs. So we can see the one that is accounting for both drag force and gravity is much more linear than the other two, and we have the tracker graph looking like so, more similar to the one that only. Some questions that could arise here is that looking at the velocity versus time models generated by GlowScript, which one predicts a terminal velocity? So by looking just at these graphs, we can see that accounting for drag and gravitational forces predicts a terminal velocity. That graph is the one on the right. The terminal velocity is a point at which drag force, which points up, cancels out the gravitational force pointing down. This means net force at that point would equal 0 and lead to a terminal. Another question could be what if the object was thrown downwards instead of just dropped? Would this lead to the terminal velocity being the same or differ from our conditions in the experiment? So the answer to this is that it would only change the initial velocity of the object being thrown / dropped, and so the terminal velocity would remain the same in both cases. This is because terminal velocity is only affected by gravitational force plus the weight of the object. So because those things didn't change, the terminal velocity would remain. So some experimental errors that might have been possible during this lab are the ball did not fall completely straight. My hand dropping it was not completely steady and could have had a slight push when dropping the object. Miscentered tracking points and rounding errors also could have occurred. Thank you for watching.